So we can start with questions. Does anyone have any questions for the panel?
Okay.
I have a bunch here, right?
Okay.
Rather
Okay.
not ask them all, but
How does it work? That's the first
you
question.
turn that on. Push up the button.
It is, but it does.
Yeah.
So my first question would be to the audience, because I have no clue who's in the audience. Who in the audience is developing distributed analysis software for next generation sequencing data? Who dreams of developing distributed distributed analysis software for next generation sequencing data? So who is dealing with next generation sequencing data? So what are the others doing who are here? If they are not in distributed computation and not in next generation sequencing, you are just here for curiosity. Okay, fine. So those who deal with next generation sequencing data but not with distributed analysis software, why don't you deal with distributed analysis software? Speak up. So you have no runtime problem.
Not very much. No.
Okay.
That's the problem of thinking and analyzing and looking at the data and getting the biological annotation is much, much more than what we have. And I think even if we have much more data, still the biological part will be much more. That's also the processing and the writing of the data.
Yeah. Maybe somebody else? Not really. Okay.
To what extent will bioinformatics pipelines be rewritten for Hadoop, and what will the new APIs look like? So I'd like everyone to answer the panel and start wherever, in whatever order. Just to introduce, we have two members to ask already. Mikael Huss from ScifiLab, hand up, people know you are. And then we have Huss from
So we just decided to start on the other side.
Okay, so the question was to what extent
will we, if we look 5 years, 10 years out, to what extent will we rewrite bioinformatics pipelines for big data platforms such as Hadoop, Spark, whatever? And then what will the new APIs look like? And this is good for you because Mikael has written 3 blog entries recently which are very interesting on these different new APIs, including genomics API.
Yeah, I've written 3 blog entries with just some notes on how to use 3 different genomics APIs. One Codex API, which is a metagenomic, or really a generic sequence classification API. Google Genomics, which has been discussed here a little bit, which is mostly concerned with retrieving variant data, I would say, right now. And Solve Bio, which is an API for, well, how to summarize it? Well, it's also geared towards variant analysis, I would say, on GWAS and things like that. But to the question, well, it's really hard to give a number, of course. I think to some extent we can escape rewriting some things because the methods and algorithms are changing all the time anyway. So for a lot of things, maybe you can just write it. Like when a new need arises, you can just write it in Spark or whatever. But for things that kind of work and that need to be rewritten, well, it's a little bit like the audience comment we got in the beginning that some I mean, some things are very exploratory, so you don't know exactly maybe what you want to do, so you need something that is a bit more more interactive, like more of a shell thing, maybe, where you explore different things, which could be something like Spark maybe as well. But then, of course, you might, then there's another type of software which is more the backbone software, like mapping, read mapping, and so on, which might have to be written. Okay, I'll.
Yeah, so I guess, so I guess I'll kind of agree with him there. I don't think that you'll necessarily be rewriting many things. I think it's rather, yes, the next time that you write things, you will rethink them. I mean, we ourselves are doing a lot of rewriting of things at Berkeley, mostly as a proof of concept for how to do, how to novelly write these algorithms on a novel distributed computing system. I think the big thing is that we have to, kind of as a field, rethink how we are expressing these algorithms. It's like there is a fair amount of interest right now in the genotyping space around the GVCF. So saying, hey, I'm not going to go ahead and purely, if I want to joint call one sample with all the information I've gotten from all my other samples, from the past 1,000 samples that I've seen, I'm not going to load up the reads for 1,000 samples and then recall them. Instead, I'm going to load up the GVCF for 1,000 samples, load up the reads for this one novel sample that I've seen, and use that to do the processing. And so from the perspective of computational efficiency, this is wonderful. From the perspective of, are we losing information that we could recover if we loaded up all 1,001 samples, raw reads and did the calling there? That's not clear. So, there's actually a few folks that we've spoken with in the clinical side who believe that, we're losing information. There's a few people I've spoken to on the method side that believe that we are losing information when we go to these GVCF approaches. I think that we're going to have to rethink how we do method development. We're going to have to rethink how we do multi-sample processing. And I think we're going to have to really understand statistically what we're really doing when we integrate across multiple samples. Because I think that's really what drives this, drives going to large clusters. You're either going to a large cluster because you have many samples you want to process at the same time, or because you have a really tight time frame. I guess that's my thoughts.
So I think I will talk about how you would get adoption by sort of the more mainstream genomics groups, because I work largely with the Sanger, the EBI, even say Broad and WashU, who have large production factories that produce sequencing, but they're inherently, because they have validated protocols, are fairly conservative about adopting something new. So I think the first thing is you need to prove equivalence to current pipelines and show that you can get the same result. And if the results are different, to be measured very carefully, because you're not going to want to adopt a new algorithm that may have some bugs. So first you need to prove equivalence and then show that you can do the same thing in a distributed way. I would say to ease the transition, you're going to have to make sure that you have software products that aren't in alpha, but the audience that will be adopting these and running them locally have, they have experience with LSF, some distributed computing, some, running lots and lots of Perl scripts on a cluster, and they'll have basic Unix knowledge. So I think that you can target that audience, but they're going to need a much more refined, installable package if they want to be the clients of that software, not the developers. And most of the projects, I think, right now are in the alpha stage. So making that transition will be a big deal. And finally, I think you need to sell the economics of this, because there is a lot of money even in just research genomics now, and they are realizing they have to spend a lot of that money on compute. And if you can show that you can use your compute more efficiently, actually have a smaller cluster, but they do the same amount of work, because many of these clusters now are operating at 5% use much of the time, show that it's an economical choice and they should be investing in the research that you all are doing.
So to come back to your question, it's a difficult question. I can actually think of just 2 tools that were written with the idea of running on a distributed system just right from the start. So one is Abyss, by J. Rit Simpson for de novo genome assembly, which was written using MPI. So basically, memory was a bottleneck when doing de novo assembly. And the other one is Adam, right? So that's basically rewriting a whole variant calling tool, taking into account the fact that it should run on a distributed system. So we took the engineering approach with Halv8. So we said, okay, BWA is a tool that's being adopted by the community. It runs well, even multi-threaded. GATK is also something with a lot of domain knowledge. It's not something that you're going to rewrite easily or that you would want to rewrite. Even if you did, you'd have problems of having it adopted by the community. So we had some kind of engineering approach where we had a wrapper around these tools to go to multi-node performance. So in the ideal case, when people are developing new methods, they would want to take distributed computing as one of the main features into consideration from the start, right? Or just at least write their algorithms in such a way that there is at least an opportunity for parallelization or moving towards distributed computing in a later phase. Because I'm sure that at a certain point this will become a necessity. I heard you talking about bacteria, I think, and there is no need to go to distributed computing for bacteria. That might be true if you're sequencing single strains, but if you're going to metagenomics and stuff like this, it might really become an issue, right? Okay. Okay, thank you.
Yeah, so my take on this, I think people rely a lot on existing workflows and on those tools being available. So it's very hard to do kind of, let's say, clean plate designs in this area. You have to, in order to get published, you have to use best practices that have been developed by some of the larger players in the field. And because of this kind of the wrapper approaches, which that Halv8 is an example of, I think they are easier to push into mainstream. But that doesn't mean we shouldn't be taking kind of larger steps to say, okay, this is not the right way to do things. Let's do a clean plate design and think, okay, how can we do this better? There's lots of things like there's hidden assumptions in the tooling, like we heard in the Halv8 talk about these, let's say, variants not being identical because, well, there was some statistics that were gathered from a slightly different set of data than what's done in the parallel setting, and it would be helpful to have, let's say, variant calling tools that would have some kind of invariance on okay, they actually are doing their decision based on a finite surrounding, some kind of a sliding window of sorts. So having those kinds of things were in order to parallelize, you have to have a finite surrounding area in which you operate in order to have reproducibility in sequential and parallel case is needed. And maybe that could be something that people could be convinced of, even for sequential things. But then, of course, one of the things that shouldn't be kind of underestimated is the amount of interesting stuff that's being done on the data warehouse side. So there's a huge amount of effort being put into petabyte scale data warehouses on the, let's say, the web side of big data processing, and just reusing all of that software, be it machine learning, be it, let's say, good frameworks for parallel querying, be it good file formats. I think those should be exploited, and currently we're kind of just redoing the same stuff. Instead, we should think, okay, now we have these nice hammers. What could we do that hasn't been possible to do before. And maybe that's all I have on this topic.
Yeah, so that's, of course, it's a difficult question. So I entered the field of bioinformatics, I think, in '98. So it's now 16 or 17 years. And over these years, the computer science community has always been very good in telling bioinformaticians that they are doing it wrong. So they did it at least 10 or 15 times. And usually they had kind of zero impact. And so I myself come from data integration, so there have been hundreds of papers in the computer science world how the biologists could do data integration better, and they never listened to it, and they still don't listen. And one reason is that that these people, and me now as well, are very, very practical. And very often, if you wait 2 or 3 more years, you don't need all these complicated methods. Because either the machines are more powerful, or the data has changed, or the algorithms are so much faster. So if we think of BWA, that's a nice example. I think it was published in 2010. It's still a lot in use, but there are read mappers that are 100 times faster on a single core. They are just not used as widespread as there's BWA, because the whole community is a little bit conservative, or very conservative, I don't know. But at some stage, there might be the point where they think, okay, should we have a parallel BWA, or should we just use Razor M, which has the same speed without all the hassle of a distributed setup? But I might be totally wrong, because there might be an end of free lunch, and the data will grow now really, really faster than the algorithms can scale up. But there's also a lot of work in data compression, so we work in compression, and you can really, much of the data you can very efficiently compress, and you can search these compressed archives. So at the end, I think we need distributed computing, but maybe not this 10,000 node computing that Google needs for web archives. Maybe we will always be fine with 10 or 15. Yeah, so I think trying to re-implement these things is really is not going to work. There are just so many people in parallel working on new versions of all the different sub-problems that we can think of. That it will be very difficult to convince them.
More or less on this line. Basically, bioinformatics, as it's usually considered, it's a very conservative business. That in part comes from the fact that if you want to compare what I've done with what you have done, you need to have a certain set of things which you agree upon. So we have, for instance, the usual thing is that we use BLAST version, so and so. We use this specific version of BWA. So basically, you have to express in a very concrete and down to the version number the specific steps you did in your pipeline. That's one thing. The second thing is that usually people that are involved with, say, NGS or things, usually are tend to have at the same time, let's say, to be mostly bioinformaticians. I mean, people who are actually running the pipelines. So they tend to run whatever they were running the day before. They tend to build their own things, all right? And this sort of makes things even more conservative in a way, because then you have to drop what you did before and then do it. So unless you have a very strong reason, it's usually it's not that easy to sell the fact that you have to change whatever is the paradigm you're using for your computation. This said, I think there are 2 things which are on the other hand moving in a different direction. The 2 things are, one, that actually you're getting more and more clinicians. I mean, people who are involved in trying to understand what is contained in their biological samples, they know they can use a next-generation sequence. They use next-generation sequencing, but they don't really have basically, they're not really interested in the algorithm development. They just want to use something, okay? And these kind of people also tend to use workflow system of some sort, which implies that there is a facade. I mean, there is some sort of shielding between what you are running and what is actually run. So that's one thing. The second thing, the same kind of movement it's toward in real clinical application. The real clinical application will be on one end something where things will stabilize. So at certain points will be more important to have a sort of a an efficient version of that, and the second of a specific software pipeline. And at the same time, probably these things will be done in a way that will scale. It's not like a single machine running in a single lab, or I mean, on the specific department, university department, but mostly will be the university. I mean, sorry, the hospital facility or a group of hospital facilities. So at that level, of course, they will need to have. I mean, things will not scale if you don't have the distributed, scalable solution on the back. So I think what it comes down to is that probably there will be. I mean, I'm expecting to have a stronger development of distributed approaches on building pipelines and doing whatever that's to be done from the point of view of the software. Probably they will. I expect it to be aimed. These things will aim not really to satisfy the needs of the bioinformatician next door, but rather to a different audience. I mean, part of the reason why everybody, I mean, the typical things, which, by the way, I think is right. Bioinformaticians are doing, generically, they're not doing it right from the point of view of computer science, but that's a different question. So, but the reason why telling them, well, you shouldn't do this way, you should do it in a better way, was really because there was no real incentive behind. I mean, an incentive like, well, an economic incentive makes a difference. Situation where you're running production and you really want to make things that will be cheaper in some sense, or more consistent, or whatever, will actually have an impact. So effectively, if you're not trying to convince, as I said, the bioinformatician next door, then it will make sense. I mean, then it makes sense. Then it's a target you can try to get. On the other hand, probably that means that at a certain point these things will converge to a finite small number of possible solutions, because at a certain point will become clinically used, and at that point you can't touch anything more, or at least you don't really need, you cannot really think of having a very fast development cycles or whatever. Okay, that's 2 cents. Well, well, they're not. It's not like they're telling the bioinformaticians. It's like the user community wants to have that service at a certain point, so they have to arrange so that. But no, I mean, I only know what happened to us. In our case, being able to automatize and being able to run things using the distributed. I mean, basically to have parallelized alignment and all the processing done parallelizement, just paid off. In the terms of maintaining with a reasonable, okay, let me put it this way. The real difference between what we were doing before, which was using standard, basically distributed in a sense the grid engine was doing the distribution, the low distribution kind of approach for computing, which is in a way similar to what ABI was running at the time, to something where we use Hadoop as a backend. Really helped us a lot from the point of view of reliability of the system, of the maintenance of things. I mean, so you have a more robust, reliable, and scalable approach to do things. And that implied that we ended up having that plus more precise, I mean, sort of a better automatization brought us from having to pay 4 people to run, 3 people to run the thing, to having 1. And then using the other 2 to do something else. Okay, so I think the problem is if you're a really large place like EBI, probably you have. I mean, just to use EBI as an example, you already have a long history of running these things. So you have a lot of investment, a lot of things that you need to be changed. I mean, probably have thousands and thousands of Perl scripts that if somebody goes and touches something somewhere, then it can break production, so you have to be very, very careful. If you do it from scratch, then I think that will be the way to do it. And that's our experience, basically.
What tools will we be using? Bioinformatics is not a static area. A lot of people use Perl and still do, but they've moved to Python a lot. You know, in 10 years, what will the tools be as well, the languages? I mean, will it be Scala? Will it be Python and Spark? Will it be, you know, where should the efforts go for the community?
It depends.
10 years.
Will we
have computers in 10 years.
Yeah. Well, so yeah, I think so. I don't know necessarily what the what languages folks will be using. Yeah, it's like languages come and go all the time. I mean, a few of them have sticking power, but I do think one of the things that I'm excited for over the next 10 years that we'll see play out is whether we move from short reads for some analyses to long reads. And I think if one, the methods come along, and well, actually, if one, the sequencers come along, and two, the methods come along, then I think we'll be looking at a very different ballgame. Right? It's like we talk about Illumina being very cheap per base, but if you look at a technique like Oxford Nanopore, not only are they extremely cheap per machine, but they're also, they're really competitive on a per base level. The data is completely different from what we've been dealing with right now. And so I don't know. I think that's an interesting thing to look out for. I mean, the methods will be completely different. From an analysis perspective, what I would guess is that you're going to see a lot of the people who are kind of hacking around at terminals right now move to kind of nicer interactive systems, whether it's something like an IPython notebook or whatever the IPython notebook of 10 years from now looks like. That's actually something that we're really starting to focus on. And Atom is, we have this project that we're ramping up called Mango, which is, uses a Spark notebook on top of Atom so that you can do kind of interactive genome visualization, cut down on feedback loops. And I think that'll be really useful for, ideally people who are on the scientific side who have a bit more programming literacy, kind of these data scientist folks who want to analyze their data more. But yeah, in terms of what we'll be building tools in, I don't necessarily know. I mean, I think the programmer or the computer scientist in me wants to say that managed languages are the way forward and that C++ will probably die off. But historically speaking, anybody who's bet against C++ has been wrong. So
what's a managed language?
So managed language would be, something that runs inside a VM or interpreter. So, Java inside the JVM, or any JVM-based language, Python, Ruby, etc.
I can just comment quickly. So I also very much endorse the IPython notebook type way of working. I mean, regardless of whether it will be IPython notebook, because it's interactive, reproducible, and shareable. So yeah, I think that's good.
So just a side note, but what I would expect in a couple of years, especially when medical applications become more and more important, and I mean, taking Germany as an example, so you cannot get grant money without a medical application at the moment. You need MDs in your project or you will not be funded. But I think what will be important is that companies will jump in. So medical doctors will not fiddle around with our software. It's all not nice enough and not stable enough. So there will be companies offering this as a service. And these companies will really look at total cost of ownership. I don't know who's going to win, but it's the amount of machines that you have to buy, the amount of manpower that you need for maintaining it, and the amount of consultancy that you have to give to your clients to have them analyze the data. So I don't know. So SAP, for instance, at the moment is pushing hard into this market, not with a distributed system, but with its main memory database running on 80 cores on one machine. And they try to make money out of this. I don't know if they will be successful.
I remember that when I was a graduate student, the idea was no matter what language would have been, actually before when I was an undergraduate, no matter what language would have been, but it would have been called Fortran. So that doesn't apply. So probably NS are probably doing that.
open source alternative now. I mean, that the community is aligned on. Will we align around the global, or this global alliance for genomics, or how do people see it playing out? I mean, normally we have one or two players. Computer science programs, we have one big player and one second player. But what player do we have?
Yeah, well, so there's a few things I would say, and so one is that there are actually a few companies out there that are pushing, open source products. So the two notable ones, well, the two ones that I know of would be, Arvados / Curaverse and Seven Bridges Genomics are both pushing systems that are, vaguely similar to what DNA Nexus is going for, but that are, open source. And then I think if you go in-house, they then provide, help with management and whatnot. And what I will say, along the Global Alliance side is that, all of the 4 companies that you've mentioned there, except for, there's no one that I know of from the Illumina Base side who's involved in the Global Alliance Data Working Group. Everyone else who's just been mentioned in these last few sentences is involved. Although, the way that I'm seeing it is that the Global Alliance, we're hoping to make a impact on how people describe workflows and to make sure that workflows are portable, from say from DNA Nexus to Google Genomics to Arvados to Galaxy to insert tool name tool X here. And we're also very interested in the data interchange, the data interchange story, but I don't think that'll necessarily impact how people are writing analytics. I think it'll mostly have an impact on how people warehouse and share data and how people define analyses, like analysis pipelines.
They talk about it constantly as a solution to the problem of larger sample sizes. How far what's the level of interest and technical interest in
I'll answer a very closely related question. Is that I would say that if the technologies don't exist now, then they really need to, because there's a major policy sort of national data sharing issue that would be solved if you could avoid having to move data to a centralized location where it could live, in a cloud in each nation, but then you could ship pieces of work to each place where it could be computed, but then recombined later at an aggregate level that wouldn't violate all of these data sharing restrictions of passing personal level genomic data between nations. So I would say that even if it's technically a real pain, we really need these kind of federated solutions, because otherwise there's going to be legal type issues that prevent science from being done.
Will the law change? When people, like we had a smoking ban which was introduced globally pretty much, and people said it'll never happen. And then when we saw the benefits of it, everyone said, I want that. But will the law change and federated never happen?
Oh, you're saying the drive for federated would go down if the law changed and made it easier to share data? Yeah. Well, so the trajectory kind of isn't looking good in Europe right now. It actually might get worse in terms of sharing this data around. So I think it wouldn't be a bad idea to plan for the worst and make sure that some federated solutions do exist.
We're running out of time.
I will not comment on SAP's kind of database, but I think in-memory databases in general are a good idea if your data volumes allow that. They are just immensely more faster than any SSD or hard drive based solutions. So be it then, let's say Spark SQL or SAP or whatever, if the data set is small enough, yeah, you should go for in-memory solutions.
Just a little anecdote. So don't quote me on this, but so SAP HANA had a research prototype with Charité and a research project to build a prototype. And it was on data integration and data analytics, and there was access with a tablet, and you could browse through data in real time, and there was a whole processing engine in between, and it was main memory, column-based, compression, blah, blah, blah. And if you go to anybody at Charité and tell them, do you know about this SAP? They will say, oh yeah, cool, that was with a tablet. So, and such things will be really important. So if we speculate about whether a company like SAP is successful in this market, it will be a lot on user interfaces, knowing the CEO, and not so much on technical advancement. Especially, I mean, in bioinformatics, we all publish everything that we do. It's all open source. They just have to grab it and re-implement it. So they don't need to be a genius to develop a new fastest read mapper. They just re-implement one that has been published. And then it's about user interfaces and connectivity into the medical data, into the hospital information systems. And if this will be successful, I have no idea. I have no SAP shares.
So I'd like to